If I handed you a recipe that just said eggs, flour, sugars with no amounts, you'd never bake a cake. That's exactly what an unbalanced chemical equation is, a useless recipe. It tells you what goes in and what comes out, but not how much of each. Today we're going to turn that useless recipe into a precise one. We'll see what a chemical equation really is, why getting the numbers right matters so much, and how chemists count invisible atoms using a unit called the mole. Then we'll work through an example together and dodge the most common mistake people make. A chemical equation is just a recipe written in symbols. On the left, before the arrow, you list your reactants, those are your ingredients. On the right, after the arrow, you list your products, the finished dish. The arrow itself simply means a makes for yields. So hydrogen plus oxygen makes water is written as H2 plus O2, arrow, H2O. Imagine baking bread and guessing the flour. Too little and you get soup, too much and it's a brick. Chemical reactions are the same. If you don't know the exact amounts, you might run out of one ingredient halfway through, wasting the others, or leave dangerous unreacted chemicals in your mixture. In a lab or a factory, that's a disaster. Atoms are ridiculously tiny, you can't just grab a handful and count them. So chemists use a counting unit, just like a baker uses a dozen for eggs. It's called a mole. 1 mole is a very specific number, about 6.02 times 10 to the 23. That huge number lets us scale up from invisible atoms to grams we can actually weigh on a balance. 1 mole of carbon atoms weighs exactly 12 grams. Let's fix the recipe for water. We start with H2 plus O2 makes H2O. Count the atoms. On the left we have 2 hydrogens and 2 oxygens. On the right, 2 hydrogens but only 1 oxygen. An oxygen atom has vanished, that can't happen. We need 2 oxygens on the right, so we put a big 2 in front of H2O. That gives us 2 water molecules, which means 4 hydrogens. To balance, we put a 2 in front of H2 on the left. Now we have 4 hydrogens and 2 oxygens on both sides. Balanced. The biggest trap is changing the tiny subscript numbers. You might think, I need another oxygen, so I'll turn H2O into H2O2. But that's no longer water, that's hydrogen peroxide, a completely different chemical used for bleaching hair. It's like changing the word flour to flour to fix your cake. You must only ever change the big numbers in front, the coefficients, which tell you how many of each whole molecule you have. You can't count atoms one by one, but you can weigh them. How do chemists know exactly how many atoms are in a beaker without ever seeing them? It's like knowing how many pennies are in a jar just by putting it on a scale. If you know how much 1 penny weighs, the total mass tells you the count. That's the trick we're going to learn. We're going to build a bridge between the invisible world of atoms and the world you can measure in the lab. First we'll see what this bridge actually is, a simple conversion method. Then we'll see exactly how it works, using water as our first example. After that we'll walk through a full calculation with carbon dioxide, and finally we'll look at 2 mistakes that trip people up, so you can avoid them. You already know a mole is a specific number of particles, an enormous count, like a chemist's dozen. Now, every substance has a molar mass, that's the mass of exactly 1 mole of that substance, in grams. You find it on the periodic table. For an element, it's the number under the symbol. For a compound like water, you add up the molar masses of all the atoms in it. The mole bridge is simply using that molar mass to convert between the count of moles and the mass in grams, like knowing 1 brick weighs 2 kilos lets you convert between number of bricks and total weight. The conversion is just multiplication or division, but the key is watching the units. If you start with moles and multiply by grams per mole, the moles unit cancels out, 1 on top, 1 on the bottom, leaving you with grams. If you start with grams and divide by grams per mole, the grams cancel and you're left with moles. Think of it like turning a map direction into real steps. If 1 centimeter on the map equals 100 meters in the real world, you multiply map distance by 100 to get real distance. The molar mass is that conversion factor. Let's use water. 1 mole of water weighs 18.02 grams. So 2 moles weigh 2 times 18.02, which is 36.04 grams. And 36.04 grams divided by 18.02 gives you back 2 moles. Let's work through a full example. We want the mass of 2.5 moles of carbon dioxide. First we need the molar mass. Carbon dioxide has 1 carbon and 2 oxygens. From the periodic table, carbon's molar mass is 12.01 grams per mole, and oxygen's is 16.00 grams per mole. So we add 12.01 plus 2 times 16.00, which gives 44.01 grams per mole. That's our conversion factor. Now we multiply 2.5 moles times 44.01 grams per mole. The moles cancel, and we get 110.025 grams. So 2.5 moles of carbon dioxide weighs about 110 grams, something you could actually put on a balance. 2 mistakes happen all the time. First, grabbing the wrong number from the periodic table. The big number at the top is the atomic number, that's just the count of protons, not the mass. You need the decimal number underneath, the atomic mass. Second, flipping the conversion factor upside down. If you multiply grams by grams per mole, you get grams squared per mole, a nonsense unit. Always check that the units cancel to give you what you want. If you want grams, the moles unit must cancel out. So the whole idea is, the mole bridge is just multiplying or dividing by the molar mass, and watching the units keeps you on the right path. You can't count individual atoms on a lab bench, but you can predict exactly how many show up to the party. The secret is hidden right in the chemical equation. It's like a recipe that tells you the exact number of each ingredient you need, not in grams, but in particles. We're going to unlock the central method of stoichiometry, the mole ratio. First, we'll define what it is. Then, we'll see exactly how to build one from the numbers in a balanced equation. After that, we'll walk through a real example, and finally, we'll look at the mistakes that trip people up, so you can steer clear of them. A mole ratio is a conversion factor built directly from the coefficients of a balanced chemical equation. Remember, coefficients are the big numbers in front. They tell you the fixed recipe in moles. The mole ratio takes those numbers and turns them into a fraction that links any two substances in the reaction. It's a bridge that lets you cross from the moles of one thing to the moles of another. Here's how it works. Look at the balanced equation. The coefficient in front of a substance tells you how many moles of it are in the reaction. For example, the 2 in 2H means 2 moles of hydrogen. To build the highway, you take the coefficient of the substance you want to find and put it on top, and the coefficient of the substance you're starting with on the bottom. When you multiply, the demoles of starting substance units cancel out, and you're left with the moles of desired substance. It's a simple, powerful unit conversion. Let's put this into practice with the combustion of propane. The balanced equation is 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. Suppose we start with 2.5 moles of oxygen and want to know how much carbon dioxide is made. We build the mole ratio from the coefficients. For every 5 moles of oxygen, we get 3 moles of carbon dioxide. So our conversion factor is 3 moles of CO over 5 moles of O. We multiply our starting amount, 2.5 moles of O, by this fraction. The moles of O units cancel, and we do the math. 2.5 times 3/5 equals 1.5 moles of Co. That's our answer. Watch out for these common mistakes. First, don't reach for molar mass here. The mole ratio is for converting between moles of different substances, not between moles and grams. That's a different step. Second, be careful not to build the ratio upside down. If you want the oxygen moles to cancel, the oxygen coefficient must be on the bottom. If you flip it, the units won't cancel properly, and you'll get a nonsense answer. Finally, this whole method only works if your equation is balanced. An unbalanced equation gives you the wrong coefficients, and therefore the wrong ratio. So, the whole idea is, a balanced equation gives you a precise mole-to-mole conversion factor, a direct highway from any reactant to any product. You start with grams of one substance, and you need grams of another, but the periodic table doesn't give you a direct conversion. The secret bridge that connects them is the mole, and skipping any step will give you the wrong answer. We'll see what mass-to-mass stoichiometry really is, break down its 3 essential steps, walk through a complete calculation from start to finish, and then look at the 2 most common mistakes so you can dodge them. Mass-to-mass stoichiometry is the 3-step process that takes the mass of a starting substance, the given, and finds the mass of a substance we want to know about, the unknown. Because there's no direct gram-to-gram conversion, we use the mole as a middleman. It's like changing money. You can't swap dollars directly for yen without knowing the exchange rate, and here the mole is that rate. The chain has 3 mandatory links. Step 1 uses molar mass, the mass of 1 mole of a substance from the periodic table, to convert grams of the given into moles of the given. Step 2 uses the mole ratio from the balanced equation. The coefficients tell us how many moles of unknown come from each mole of given. Step 3 uses molar mass again, this time for the unknown, to turn moles back into grams. Every mass-to-mass problem follows this exact sequence. Let's solve. How many grams of water are produced when 32.0 grams of methane burn in excess oxygen? First, find the molar mass of methane. Carbon is 12.01, for hydrogens add 4.04, so 16.05 grams per mole. Divide 32.0 grams by that to get 1.99 moles of methane. The balanced equation says 1 mole of methane makes 2 moles of water, so multiply by 2 to get 3.98 moles of water. Finally, water's molar mass is 18.02 grams per mole, so multiply to get 71.7 grams of water. Units cancel at every step, leaving us with grams. The 2 most frequent errors are using the mole ratio upside down and stopping after finding moles of the unknown. If you flip the ratio, you might accidentally say 1 water makes 2 methanes, which makes no sense chemically. Always check, does the substance you want to cancel appear on opposite sides of the fraction? The second mistake is forgetting step 3. Moles of unknown is not the final answer, you must convert all the way to grams. So the whole idea is, grams to moles, moles to moles, moles to grams, never skip a step. You have enough hot dogs for 20, but only 15 buns. How many complete hot dogs can you actually make? Chemistry follows the same ruthless logic. In a reaction, one ingredient always runs out first, and that's the one that calls the shots. Here's the plan. First, we'll define what a limiting reactant really means. Then we'll see how the mole ratio from the balanced equation acts like a detective, sniffing out which reactant runs out first. We'll walk through a concrete example making water, flag the mistakes that trip people up, and finally peek at how to calculate the leftover excess. The limiting reactant is the ingredient that gets completely used up first in a chemical reaction. Think of it as the guest who eats the last slice of pizza. Once they're done, the party stops. no more product can form, no matter how much of the other reactants you still have lying around. It puts a hard cap on the maximum amount of product you can make. Here's the trick. The balanced equation is your recipe, and the coefficients are the mole ratios. For each reactant you have, use that ratio to ask, if this reactant were used up completely, how many moles of product could it make? Do this for every reactant. The one that produces the smallest amount of product is the limiting reactant, it's the bottleneck. Let's make water. The balanced equation says 2 molecules of hydrogen react with 1 molecule of oxygen to give 2 molecules of water. Suppose we start with 5 moles of hydrogen and 2 moles of oxygen. Using the mole ratio, 5 moles of hydrogen could produce 5 moles of water. 2 moles of oxygen could produce 4 moles of water. Oxygen gives the smaller number, so it's the limiting reactant. It runs out first, and we can only make 4 moles of water. Watch out for 2 traps. First, never just compare the masses of your reactants. A big pile of one thing doesn't mean it's in excess, because molecules have different weights. Second, don't assume the reactant with the smaller coefficient in the equation is automatically limiting. The only way to know for sure is to do the mole ratio calculation for every reactant and see which one makes the least product. Once you've found the limiting reactant, the next natural question is, what about the other guy? The excess reactant. You can calculate exactly how much of it is left over by figuring out how much actually reacted with the limiting reactant, then subtracting that from what you started with. It's like counting how many hot dog buns are still in the bag after the franks run out. So the whole idea is, the limiting reactant is the bottleneck that sets the maximum product, and you find it by letting each reactant take a turn at the mole ratio bridge. You carefully mix your chemicals, filter, and dry your product, but the final mass is always less than you expected. Where did the rest of the reaction go? It's not magic, it's real-world loss. We need a way to measure how much of our product we actually managed to keep. Today we're going to learn the chemist's efficiency report card, percent yield. We'll define what theoretical and actual yield are, learn the simple formula, walk through a real calculation, and see what mistakes to avoid. By the end, you'll know exactly how to judge if a reaction was a success or a messy loss. Theoretical yield is the maximum amount of product you could possibly make, calculated from your limiting reactant using the balanced equation. It's the perfect world number. Actual yield is what you physically weigh on the balance after the experiment, always less, because some product gets stuck on filter paper or left in beakers. Percent yield is just the fraction you actually got, turned into a percentage, like a test score for your reaction. It's a 3-step recipe. First, you already know how to find the limiting reactant, that's the one that runs out first. Second, use that limiting reactant and the mole ratio from the balanced equation to calculate the theoretical yield in grams. That's your perfect score. Third, take the actual yield you measured in the lab, divide it by that theoretical maximum, and multiply by 100. The answer tells you what percentage of the product you successfully captured. Let's run a real example. Say we start with 5.0 grams of reactant A, and B is in excess. Using the balanced equation and molar masses, we calculate that the maximum possible product C is 4.0 grams. That's our theoretical yield. But after the reaction, filtering, and drying, we only collect 3.2 grams. So our percent yield is 3.2 divided by 4.0 times 100, which gives us 80%. We lost 20% of the product along the way, maybe stuck to the flask, or lost during transfer. The biggest trap is calculating theoretical yield from the excess reactant, that gives a number way too high, because there's leftover excess that never reacts. Always use the limiting reactant. Another mistake is getting a yield over 100% and just writing it down. That's impossible. It means your product is wet, impure, or you misweighed something. Always question a yield above 100%. And don't forget to convert everything to grams before you plug into the formula. Without percent yield, you're flying blind. A mass of 3.2 grams means nothing by itself. Is that good or bad? Percent yield tells you. If it's low, you know you lost product during filtration or transfer, and you can improve your technique. If it's consistently high, you might have impurities. It's the difference between just doing a reaction and actually understanding how well you did it. So the whole idea is, percent yield turns a raw mass into a meaningful efficiency score. Every time your car's airbag saves a life, a precise chemical calculation made months before on paper determines exactly how much gas fills that bag in a split second. Get that calculation wrong, and the bag is either a rock or a puff of air. We're going to see how the mole ratio method you've learned becomes a superpower for solving real problems. We'll define what applied stoichiometry really means, walk through the three-step bridge that connects any starting amount to any product, then calculate the exact grams of chemical needed to fill a real airbag. Finally, we'll flag the two traps that catch beginners so you can step right over them. Stoichiometry is simply the math of chemical recipes. Just like a cooking recipe tells you 2 cups of flour plus 1 egg gives 12 cookies, a balanced equation tells you how many particles of each ingredient combine and how many particles of product you get. Because we can't count particles one by one, we use the mole, a chemist's counting word for a huge, fixed number of them. Stoichiometry uses the mole ratios from the balanced equation to predict exactly how much of any substance will be used up or made, whether you measure it in grams, liters, or even truckloads. The method is a 3-step bridge that works for any reaction. Step 1. Take whatever you're given, grams of a reactant, volume of a gas, even number of tablets, and convert it to moles. You do that using molar mass if it's a solid, or the ideal gas law if it's a gas. Step 2 is the heart of it, multiply by the mole ratio from the balanced equation. That ratio is the conversion factor that switches you from the substance you know about to the substance you want to find. Step 3, convert those moles of the target into whatever units the problem asks for, like grams or liters, again using molar mass or gas laws. The whole trick is that the mole ratio is the only bridge between different substances. Let's solve a real airbag problem. We want to produce 60 liters of nitrogen gas to fill the bag. The reaction is sodium azide decomposing, 2 Nan3 solids break down into 2 sodium atoms and 3 N2 gas molecules. Our job is to find the grams of sodium azide needed. Step 1. Convert the given 60 liters of nitrogen gas into moles. At room temperature and pressure, 1 mole of any gas occupies about 24 liters, so 60 liters is roughly 2.5 moles of N2. Step 2. Apply the mole ratio. From the balanced equation, 3 moles of N2 come from 2 moles of Nan3. So we multiply, 2.5 moles N2 times the ratio 2/3 gives us about 1.67 moles of Nan3. Step 3. Convert moles of Nan3 to grams. The molar mass of Nan3 is 65 grams per mole, so 1.67 moles times 65 grams per mole equals about 108 grams. 2 mistakes trip up almost everyone at first. The first is using the mole ratio upside down. You might accidentally put the given substance on top instead of the target. The fix is to always write the units and make sure they cancel. Moles of given times target over given leaves you with moles of target. If the units don't cancel, you've flipped it. The second mistake is forgetting to convert to moles before using the ratio. You cannot plug grams straight into the mole ratio. That's like trying to trade dollars for euros without knowing the exchange rate. Grams are a mass unit, the ratio counts particles, so you must always go through moles first. Convert to moles, apply the ratio, then convert back. Master these two checks, and you'll never get lost on the mole highway. You've solved for grams, moles, and everything in between, but what if every single stoichiometry problem you ever face is just for steps? Imagine a single, reliable path that takes you from a given mass of one substance all the way to the mass of another, no matter what the reaction is. That path exists, and it's built on the mole ratio you already know. In this quick recap, we'll pull everything together into a single, repeatable flowchart. We'll see what the one method is, walk through how its four steps connect, solve a complete problem together, and highlight the two most common mistakes that can break the chain. By the end, you'll have a mental tool that works for every reaction calculation you'll meet. The one method is a universal four-step flowchart that turns any mass-to-mass stoichiometry problem into a simple journey. You always start with a balanced chemical equation, that's your map. Step 1. Take the mass you're given and convert it to moles using molar mass. Step 2. Use the mole ratio from the balanced equation to jump from moles of your starting substance to moles of your target substance. Step 3. Convert those moles back to grams using the target's molar mass. That's it, 3 conversions, 1 ratio, and you're done. Here's how the chain works, step by step. The balanced equation is your starting point. It tells you the exact mole ratio between any two substances in the reaction. Think of molar mass as a bridge that converts between the world of grams, which we can measure, and the world of moles, which is the chemist's counting unit. Once you're in moles, the mole ratio is the central bridge that connects your starting substance to your desired substance. Finally, you cross back to grams using the target's molar mass. The beauty is that this identical path works whether you're going from reactant to product, product to reactant, or even between two different products. Let's apply the full method to a single problem. How many grams of water form when we burn 16.0 grams of methane? First, we need the balanced equation, CH plus 2O gives CO plus 2HO. Step 1, convert the given mass of methane to moles. The molar mass of methane is 16.0 grams per mole, so 16.0 grams divided by 16.0 grams per mole gives exactly 1.00 mole of methane. Step 2, apply the mole ratio. The coefficients tell us that 1 mole of methane produces 2 moles of water, so we multiply by 2 over 1 to get 2.00 moles of water. Step 3, convert moles of water to grams. Water's molar mass is 18.0 grams per mole, so 2.00 moles times 18.0 grams per mole gives 36.0 grams of water. The chain is complete. 2 mistakes break this chain more than any others. The first is using the mole ratio upside down. If you accidentally put the starting substance on top instead of the target, your units won't cancel, and you'll get a nonsense answer. Always check that the unit you want to cancel is on the bottom. The second mistake is forgetting to balance the equation first. An unbalanced equation gives you wrong coefficients, which means a wrong mole ratio, and every step after that will be off. Always balance before you start the 4-step chain. Here's the best part, this identical 4-step method extends to everything else you'll do in stoichiometry. For limiting reactants, you run the chain for each reactant to see which one runs out first. For percent yield, you use the chain to find theoretical yield, then compare it to your actual yield. Even for gas volumes, the only thing that changes is the conversion at the ends. You might use molar volume instead of molar mass. The mole ratio bridge stays exactly the same. So the whole idea is, master this one chain, and you've mastered the core of reaction calculations.